we get the question too often, I get the question too often, what is Otherlab? We continue to ask it of ourselves. The simple answer is we are an independent research lab. One of our agendas for having you all here today is you're smarter than us, and you have been invited in to help us define what Otherlab is. We're not good at 140-character summaries, so we're going to give you a 2-hour summary of Otherlab. We will read your tweet streams following this to figure out what we in fact are. So a few things should happen today. You will get to see all of the projects and the companies that we are involved in and spinning up and out. You'll see our demos, but we also promise you a little more than that. We want to make you and help you think about new models of R&D and question the historic moment. And are we at an inflection point that is enabling new models of research and product development? We also want to invite you in to see how we think about some truly transformative big ideas that probably aren't on your radar, and how we are taking those ideas from fundamental research into pretty exciting products. This is probably how people traditionally think of research institutions, that they fall into 3 categories. This is really a post-World War II model where the success of the Manhattan Project and the Radar Project at MIT and Bletchley Park kind of indentured a national lab system located in sort of secure geographies. The least or the closest to being near a population center is really Lawrence Berkeley and Livermore. Corporate R&D sort of is shrinking, as you all know, and university labs became the model. Prior to World War II, there were a lot more independent labs and a lot more small corporate labs. This is where Tesla and Edison and Ford created the great things that they created. So we are arguing, really, that there's a unique moment to make the R&D infrastructure more diverse again. Another lab is an experiment in that, where we think that is enabled by the fact that research tools have become a lot cheaper. So now for $1 or $2 million, you can have pretty much one of every high-precision machine and piece of instrumentation you need to do the majority of research. And so we are exploiting that. So you no longer need enormous scale to do a lot of extremely interesting work. So to the question of what is new, and this is about as close as I'll be able to give you a sort of an intellectual theme of Otherlab. I think this is extremely exciting because it is very new. This is Robert Hooke. In 1660, he published a manuscript with this equation, F equals Kx. Only because we have a selected group would I even dare putting a equation into a talk. As our CTO, Jim McBride, says, you will lose 50% of the audience with each one. So we're going to test that. So this is what F equals Kx means. It means that we approximated all machines as linear springs and all materials as linear springs. It's literally for the last almost 400 years, we've been prisoners to this model in engineering. So we don't use materials outside of their linear regime, and we try to design all machines to operate within very linear regimes. The real world looks a lot more like this, meaning squiggly lines. And this is something that we are really working on in here. What are some of the manifestations of that? The traditional way to, these are 2 things surviving a hurricane. On the left, these are rigid, stiff, linear telegraph poles designed to take the full brunt of the hurricane. The palm trees on your right actually yield, they change their aerodynamic profile, they get rid of a lot of the forces, they are compliant, so they absorb a lot of the energy in compliance. The palm trees survive the storm, the telegraph poles don't. And this is really, I think, a spectacular and interesting development for engineering. No longer do we have to design machines to take their worst load in their lifetime. One of the fabulous evolutionary examples of this is on the left we have the tuna. It has a completely rigid, stiff tail. It was thought of as the fastest thing on the ocean. It is beaten by the mako shark on the right. The mako shark is completely soft. It's all made out of cartilage. It in fact pressurizes and depressurizes its skin to achieve enough stiffness, in fact more stiffness than the tail fin of the tuna, to be fast enough to outrun and get the tuna. So this is really an argument that we have around here, that for every machine that we have today that looks like a tuna, there is an equivalent shark that can be higher performance, whether that be cheaper, faster, stronger, one of these things. Hopefully we'll illustrate that a bunch. So Now to give you a very brief history of Otherlab, and in fact, I think it's useful to give you a little bit of history before Otherlab. So Otherlab started at the depth of the recession in 2009. It was 3 people and 1 paycheck. Jim McBride is here. He and I were not the paycheck. Don't tell my wife who's there. And really, the one thing that we brought to Otherlab was a DARPA program, research program in programmable matter. And I'm basically also going to show you a few, before Otherlab, Jim and I and many other people who now work at Otherlab were working at Makani Power. Before that, some of us were working at Squid Labs. We bought that programmable matter program. This was, DARPA said we would like the transformer, meaning the comic book version of a transformer. So we were working on the science and the theory of how you make the materials to do make transformer type machines. We were able to secure, after we left, but the progress was begun at Makani, an ARPA-E grant to progress that technology. Makani Power does high altitude wind power. So these are flying wind turbines. These are, in fact, an example of a living example. The existing wind turbine is that telegraph pole trying to survive the hurricane. Makani Power is that palm tree yielding and extracting more energy, but in a safer way. We were able to follow up the work from Program Ladder off building transformers. DARPA became interested in literally making robots 1,000 times better. Robots are not going to do, the problem was stated as we're fighting $10 improvised explosive devices in Iraq with $250,000 robots. We need to make the robots cost $25. That is the origin of the robotics work you will see here today. We also secured work under DARPA working on education. One of the greatest concerns of the DoD is that we will not have the trained individuals to maintain the physical hardware of the US military in 30 years, so they were interested in new models of vocational training. That project manifests itself today in the other machine company that we will show you. We were then able to get more work from ARPA in solar energy, in natural gas, which we'll talk about, and you can sort of see how these things cascade into work we're now doing with NASA, the National Science Foundation, etc. We hope to actually give you a little bit of an insight into those sometimes opaque research institutions. So we aren't purely research. We are very much focused on real-world problems, and I can actually draw straight lines from many of these research programs to companies or products that we sold or licensed out. Instructables started back here and was actually acquired here by Autodesk. Similarly, these technologies came directly from programmable matter, from DARPA M3, Makani Power had assistance from ARPA-E, and you can see the next generation of companies that we'll present to you today, New-Buttocks, other machine companies, Sunfolding, following on in that tradition. So here's another equation. I would like to say one thing about Otherlab. Everyone thinks that we are very playful, which we absolutely are, but I think rigor defines everything we do. I think if you're going to invest the time and your life in developing hardware, you need to be very confident that you have a fundamental advantage. So nearly every project that we have here starts with looking at some equations like this. These are actually the equations that define aerodynamic drag on a solar receiver in a desert and the stress on, or the stress on the flatness of that plate. We were able to look at this and in fact then develop this idea. This is a microhydraulic or microfluidic heliostat that tracks the sun with less than 1 degree precision. We initially proposed this, having built something almost like this to the Department of Energy, and the first response to our first proposal was, if this is such a great idea, if it worked, it would already have been done. Sorry, you can't have the money. Roughly when we received that, we started working with the woman I'm about to introduce you to, Layla Madrone. She came with a lot of experience in the solar tracking background, also having worked at NASA, and she will show you how we've gone from this sort of seed of an idea today to a very exciting deployment of real energy systems based on this technology in the field this year. Layla.
I'm Layla Madrone. I'm the CEO and co-founder of Sunfolding, and we're working on an entire new way to track the sun. A couple years ago, we got the ARPA-E award to work on exploring a lot of these ideas like the one Saul showed. And just last week, we had the announcement from the California Energy Commission that we have a grant to build our first 300 kilowatt field out in Davis this year. But it all started with a question. If you were going to build a machine just for solar, what would it look like? And in order to take a look at why you would be interested in this idea, let's look at solar itself. The solar revolution is upon us. Solar is the fastest growing energy source in the US, and in some places, it's the lowest cost energy. And this is why. Over the last couple of decades, the cost of solar has gone down to 1/100th of what it once was. And this is an incredible feat. However, the cost of solar isn't quite low cost enough to be the lowest possible energy source. And panels, you can't get any more cost reduction out of them, so we have to look at new ways to bring the cost down. So let's look at the solar ecosystem. I think when a lot of you guys are thinking about solar, you're probably thinking about something like this, solar panels on a rooftop, but this is actually only a small part of the overall solar story. The majority of solar in the US actually looks like this. Giant solar fields, utility-scale solar. And when we talk about solar coming down in price so that it looks around grid prices, this is the kind of solar we're talking about. And if we were to zoom into these fields, we'd see that 75% of the new ones have trackers on them. And so these move the panels around so they can follow the sun. And the reason we do that is with the same exact panel, you can get up to 40% more power out of it. So you can imagine if you could make a really low-cost tracker, you could really bring down the cost of solar. So let's look at what the tracker looks like. This is a state-of-the-art tracker. It's large, heavy, industrial, and compared to a sleek solar panel, it's pretty heavy-duty with a lot of moving parts. And these parts have lots of problems. Gearboxes, motors, linkages, torque tubes, bearings. We think that solar actually wants a machine that works in an entirely different way. Enter the Sunfolding tracker. So we're getting rid of all the parts I just talked about, and we're replacing it with basically a specially shaped soda bottle. And it's moved around with just compressed air. And as we change the pressure in the different chambers, we can uniquely change the position. And this is pretty exciting because we've revolutionized the materials, removed all the complexity, we've gotten rid of motors, gearboxes, bearings, and all the things we don't like that are really expensive, and we've replaced them with mass-manufactured plastic, which is extremely low cost, and compressed air. Air is also very low cost. This is a tracker revolution. So we can bring down the cost of tracking by over 50%. And to me, this is what impact looks like. I mean, for me personally, when I first got to Otherlab a couple years ago, I was a bit disillusioned about the incremental changes in the energy space. And what I've learned in being here is that if you want to make impact, you have to change some of the fundamental rules. And at Sunfolding, we're completely changing the game for tracking. Thanks.
Thank you, Layla. I'm personally extremely excited about Sunfolding because it spans our entire history as Otherlab and is a wonderful example of fundamentals all the way through to real product in the ground. One of the things I love about being involved in research at the fundamental level is the very disparate connections. This was work from 2001, 2002. This is in fact the first technical collaboration between myself and James McBride, who might wave his hand in the back, who's our CTO now. This is a piano curve. It's a space-filling curve on a 2D plane. This was work originally trying to figure out how do you make self-replicating machines. This will probably illustrate more about our personalities than anything else. This is what a Saint Bernard looks like to a mathematician. Curiously, you'll notice that the whiskey barrel around the Saint Bernard's neck is not connected. This was critical in the published proof that, in fact, you can and this, took about 100 years to go from this piece of math to this one. This was proof that you could fill any weird three-dimensional shape with a single connected piece of string. If you don't believe it on the Saint Bernard with the whiskey example, you might believe it with the gorilla. Most of our demos historically have included either a gorilla or an elephant. This is the fundamental equation. So once we figured out that you could fill a weird volume, this is the equation that defines the stress in a pressure vessel. Why we're interested in that? We're already working with the Department of Energy. They said natural gas is increasingly important in the US. We have a lot of it. It's basically twice as clean a fuel. Do you have any interesting ideas in pressure vessels? Luckily, because of where we work, we were able to connect that to this to make the technology Volute that you're about to see. This is probably the best video description that we've done.
And your best friends around. Well, cars produce pollution, both carbon dioxide and smog. If we could put a natural gas tank in your car, it would produce half as much carbon dioxide and far fewer polluting particulates. It would be greener and cleaner. So what's the problem? Typical natural gas tanks are big, round cylinders. If you try to fit them in your car, there might not be room for your best friend. It's like the classic kindergarten problem. Round peg, square hole. The world needs a conformable tank, one that fits into all the nooks and crannies of your car. At Otherlab, we had an idea. A gut feeling, you might say, somewhere in our intestines. If we made the tank super long and reduced the diameter, we could fold it up inside your car, just like your intestine is folded up in you. We are building a gas intestine for your car. It will be smaller, more efficient, and safer. Car designers will have the freedom to make cars that have room for you, your gas tank, and your best friends. The US uses around 20 million barrels of oil a day. Around 15 million of them are imported. The US has a lot of natural gas. By running cars and trucks on domestic natural gas with this technology, we will help make the US energy independent and a stronger, lower carbon economy.
And with that, I bring you Dan Rex. Thank you.
Thanks, Saul. I'm Dan. I work on the Volute project. We are building a conformable natural gas tank for cars and trucks, and I would love to tell you about how we went from that cartoon to carbon fiber. I want to put this in your car, and I want to put it in every 18-wheeler. And that's because not every bit of transportation can be electrified, and something has to be done about the carbon emissions from that sector. This is the trunk of a natural gas Honda Civic. What you can see is there isn't much trunk left after the fuel tank is put in there. Natural gas is a great fuel. It's cheaper. It's much, much cleaner, both on a pollution basis and on a carbon basis. The problem is, to get the same energy in your car, you need more than 3 times the volume. So once you put that fuel tank in your trunk, you do not have any trunk left. We want to go from that big, awkward beer keg-shaped thing to a tube that you can snake around your car. We want to make better use of available space, and we want to open up spaces that the fuel tank could not have gone in before. We are using the same materials as state-of-the-art compressed natural gas tanks. So what I've got in my hand here is a Type 4 CNG tank. Type 4 means polymer liner, high-strength fiber outer layer. The fiber holds the high pressure of the CNG, and the liner stops the gas from getting out. This means we can be certified under existing safety standards. There are no barriers to market. One feature you might notice in our design is that we use braided carbon fiber. This is a design innovation that I'd love to tell you more about at our booth. It carries a lot of advantages, both in quality and cost. We're not just doing signal segments, right? We have to do sausage links that we can snake all around your car. And we've already got a scheme for continuous manufacturing of these tanks, which is a complete turnaround from the batch processes that are used today. Let's give you a sense of the impact. This is our CNG Ford F-250. The fuel tank takes up more than 1/4 of the bed and extends above the bed walls. Take the standard tank, which holds 250 liters, and replace it with our tank, and you immediately pick up 70 extra liters of fuel storage. Take the spare tire well, which often ships empty in this vehicle, fill it with another one of our tanks, and you can take the driving range of this vehicle and nearly double it. The main consumer complaint with CNG vehicles is driving range. We can solve that problem and make the driving range of a CNG vehicle the same as a gasoline vehicle. One of the major commercialization hurdles for our technology is the safety standards, right? We need to get this thing into cars. It needs to be certified. So a lot of our actual day-to-day effort, and this is sort of letting you guys in under the hood here, is making sure these tanks can hold the required pressures. So we blow these up all the time. And eventually we're going to have to do things like light them on fire and shoot them with bullets. I'm really excited. What you see on the right of that slide is one of our tanks failing really gracefully at 10,000 pounds per square inch. These guys operate at 3,600 pounds per square inch, so we're already at the required margin of safety. We're in the process of doing our final detailed design. We're getting ready for scale up this summer. We want to get into cars, we want to get into heavy trucks, and we want to hit that part of the climate problem that Tesla can't touch. Thank you very much.
I drive a British car because of where I'm from, and I have a general derision for American cars. So my personal fantasy about this project is we are, in fact, encouraged and allowed to roll 3 F-150s in crash tests sometime in the next 18 months, which I'm looking forward to. So how do you connect natural gas vehicles to robotics? That's actually this. So the same piece of math I showed you before, space-filling curves. Not only can you fill a 3D volume, but you can trace the surface of a 3D volume with a single curve. And this is the canonical Otherlab elephant demonstrating that. This is the same elephant. We realized that we could, in fact, use the pattern created from that curve to make an inflatable elephant. Here is the inflatable elephant. And then we realized we might be able to make that inflatable elephant walk. So first we simulated a new class of pneumatic muscle. We sewed them on. And here is Stumpy, the very first soft robot to walk. It walks at the blistering pace of 1 mile every 8 hours. This was 2007, and Pete Lynn, who just had a baby, which is why he is not here. It was really he and I and Jim making this work a long time ago, and we really knew nothing about robotics. We were lucky enough, however, to meet the young man I'm about to introduce, Kevin Albert. He knows an awful lot about robotics, and he was able to bring his skills and knowledge to help us shape this into really a profound change in robotics technology. And with that, Kevin.
Thanks, Saul. Many of you are actually familiar, may actually be familiar with our technology, especially if you have kids. How many of you have seen this already?
Hello, I am Baymax. Tadashi programmed me to heal the sick and injured. You will be all right. There. I would like to help. Scan complete. You are experiencing mood swings. Diagnosis, puberty.
Whoa, what?
It's like spooning a warm marshmallow.
What do you say, buddy?
So this, of course, is Disney's latest feature film, Big Hero 6, and it's about a movie about an inflatable robot that is designed to be a healthcare companion, but of course the supervillain attacks, and it has to try to save the world. But that's not actually the point. What's interesting about this movie is they've shown us a robot that naturally interacts with the world safely, without even trying. No control systems help it do that. Just because it's soft, just because it's compliant, it is able to interact with everything around it, and you don't even have to worry. When you watch this film, you totally understand that people would be able to interact with this robot. This movie was, in fact, based on the technology from here in Otherlab, and that's how that Hero 6 came to be. But before Hero 6, you don't see robots in a world like this today. This is what you see in the world today. This is a manufacturing line. This is an automotive manufacturing line at a Ford plant, and these are big KUKA robots that are doing welding and assembly. And these robots basically are made out of rigid metal linkages. And because of that, they're very heavy, they're very expensive, and they're dangerous to be around. We have to bolt them to the ground, we have to quarantine them off from people, and we have to always bring the task that they're going to work on directly to them. We want to change this. New-Buttocks is a new class of robot that doesn't have to have the task brought to it. It can go to the task. It's entirely constructed out of compliant skins. It's pressurized with fluid to give it motion and strength, and it has no metal whatsoever inside it. This is just fabric and air, the robot you see in here. This is a controlled prototype that we did in the DARPA program that Saul mentioned. And so this robot, as a side effect, is inherently safe to work with the world around it. But what you might not expect is this robot is actually stronger for its weight than traditional metal robots. And that's because most of the high-performance material, the highest performance materials that we have access to today, are not rigid and are not metals. There are things like carbon fiber, Kevlar, and Spectra. But what we do as engineers is we constrain ourselves to this small sliver of space of rigid design. And this is because we don't want to deal with the dynamics of compliant materials and soft materials in operation. What we want to do is we want to design with rigid materials. We want to ignore the properties of materials during operation. Today, we have the ability, we have the control algorithms that we're developing here in New-Buttocks, and we have inexpensive sensing and computation that makes it possible to access this space and use softer materials in our engineering designs. These are materials that don't have to be a lot softer. These are materials like polymers, like blow-molded PET or woven nylons. We have access to the space, and because of that, we can now trade off material complexity, weight, and cost for inexpensive sensing and computation. If we look at the space of robots out on the market today, we can see the effect of our limitation, our use of rigid material and how it's constrained the industry. This is a plot of the economy of robots versus their mobile lifting capacity, and it tells a very important story. These are all the robots you would find on the market today. When we compare them to where human labor is at, we find that they actually beat human labor on economy. And it's very clear that when you can bolt them down on a manufacturing line, you can become much more efficient. But what humans are still the gold standard for are mobile lifting capacity. We are much stronger for our weight than traditional robots, and this allows us to go out into the world and do manual tasks. And most tasks today, there's a lot of tasks today that are still done that way because of this metric. What you need to do to build a robot that can get outside of the factory is you need to have the efficiency and economy of traditional robots with the mobile lifting capacity of humans, and that's what we're building at New-Buttocks. This is where we sit an order of magnitude on both metrics, which allows us to go to new environments that might look like this. This is industrial cleaning, where you need to put a robot in a rough environment. We are completely sealed robots that are non-corrosive, that you could hose down at the end of the day and bring to the task like this. Similar thing with commercial finishing, where a robot might need to go to a difficult location. Agriculture is an enormous opportunity that is completely dominated by manual labor and is losing billions of dollars of produce that is left on the field due to lack of labor availability right now. And finally, warehousing is a huge near-term opportunity, and this is where we're going first. The dynamic in warehousing today or in the past has always been pallets, and it is shifting now to individual boxes due to things like on-demand fulfillment and e-commerce. But we don't have good tools to lift boxes. We just have tools for pallets. And so right now, all of this is done by manual labor. We're the first company that's going to change this, and we're starting with heavy items because we have the highest lifting capacity for our weight than any robot that's out there on the market. We're building robots that can be retrofitted to standard pallet jacks and put on the floor of warehouses later this year. They're going to be able to lift, to help team lift tasks, which is where you're lifting between 50 and 150 pounds, and you need 2 people to do it. With our machines helping you out, you will only need 1 person. This is helpful for managers. This takes the burden off of the lifters. It makes them more efficient, and it makes them happier. This is a huge win for warehousing. This is a huge win for robots getting outside the factory and starting to enter the real world. Hope you guys come and see some of our demos and get your hands on back at the booth back here. We'll be happy to show you just how safe they are. Thanks for listening.
Maybe on your way in, you saw the one piece of the building that was painted. It's one of our roll-up doors. This is a fabulous illustration by Nick Dragotta, painted by a local sign writer, David Benzler. Nick and his wife and I have been working on comic books for more than 10 years now in a project called Howtoons. And this is a canonical example. This is actually the cover of our 10-year retrospective. This is like a 300-page book with hundreds of projects for children 5 to 12 or big children like us. There is one of these here for everyone to take home today. I encourage you to take one. If you are not going to read it to a kid or give it to a kid, then you should leave it here, and more so, you should donate enough money for us to buy a whole classroom's worth for some of the San Francisco schools that can't afford it. Anyway, I bring this up as an interesting segue. Part of doing what we do is storytelling about what is possible, and you've already seen some equations that made your eyes gloss today. Those same equations also make the eyes gloss of the venture partners and the government partners and the people who look at our technologies. And so what we've learned is that the same technology that's great for communicating to kids is great for communicating to the rest of the world. So these are illustrations that Nick draws of various things that we are working on or proposing to work on. So novel underwater robots based on Kevin's technology, This is the original drawings of the Sunfolding, and this is Nick's original visualization of what the Meccani wings were going to look like. This was drawn in 2007 and is remarkably close to what they're building today. Here are some early examples of the exoskeleton work, which I'm about to show you. Again, more robots. This was our very first proposal to take the technology that you just saw, Kevin's robotic technology, and apply it rather than being a robot that you can wear, or what we might know as an exoskeleton. So with this image, we were able to convince people, and with some of the progress in robotics, that it might be a good idea to make orthotics.
Today I am joined by researchers who invent some of the most advanced metals on the planet, designers who are modeling prototypes in the digital cloud, folks from the Pentagon who help to support their work. Basically, I'm here to announce that we're building Iron Man.
So you shouldn't actually laugh. We have the contract. We're one of a couple of teams that are, in fact, building Iron Man. Not the Iron Man that you've seen in those other comic books, but the Iron Man cartoon that I just showed you from Nick. I'm going to introduce you to Tim Swift. He is a leading world expert in exoskeletons. He's running our orthotics group, and he's going to tell you about this enormously exciting technology.
Yeah, so we start with exoskeletons, and when we say we're going to build Iron Man, every single one of you forms a picture in your head of what we're going to build, and I can guarantee you it's all wrong, right? Every single one of you, that's not what we're making. We make something that looks completely different. Our exoskeletons are made entirely out of fabric. They're lightweight, they use air to provide structure. Essentially, we can provide order of magnitude cost and weight reductions compared to conventional technologies. So I speak to this from a very unique place. My background, I was one of the lead inventors of Exo at Exobionics. So this is probably the most commercially successful exoskeleton in the world today. It's used for gait rehabilitation, things like that. These traditional devices are awesome at certain things. Primarily, these devices have started to make inroads in inpatient gait rehabilitation. They really do good things. For the first 2 years of the device, it was me and one other person were the only two who could actually run the device. So I was right there every single time when somebody got in, stood up, walked, right? The emotional high of having somebody who hasn't walked in 25 years and helping them stand up and take their first steps, right? The tears, the hugs, the family, all that kind of stuff. It's great. It's really hard to explain. The problem is with these devices, that emotional high is paired with the low of after an hour, we sit them back down, we put them in their wheelchair, and they roll out the door like nothing ever happened. And that's what every single session worked like. So that's what we're intending to fix. We want to make exoskeletons accessible. So see, the problem with these technologies is they're heavy and expensive. And it's not because we just decided to make them heavy and expensive, which surprisingly is a thought for a lot of people. It's a fundamental limitation. They're always going to be heavy and expensive, and that's the only way that we're going to be able to move forward with these devices. So what we need is a fundamental jump, a break in the way we evaluate exoskeletons, the way we're planning on making these devices. That's what we need for the future. So what we're making is, and you can see this here, and you'll see more in our demo booth, we're making this new type of device. It's all fabric. It kind of uses geometrically constrained shapes in order to transmit these loads. They're high-strength nylon weaves. And then inside them, we use a slight amount of air pressure in order to provide quite a bit of structure and stiffness, both for actuation and the passive structure as well. You can see here at 20 psi, he's able to fight with that, and it provides a lot of rigidity for something that weighs next to nothing. From there, you can kill the pressure, and it goes back to 2 pieces of fabric. That's essentially what you're dealing with. Now, we took this technology and we adapted it into kind of early proof of concepts, so people could begin to understand what are we talking about. This is an elbow flexion exoskeleton. Essentially, it's providing at 20 psi, it provides about a quarter of the peak torque of a normal human elbow. What's great about this, and just you step back from it, that's all those sound like fun numbers, but this is 1 pound in device, and it's $20 in materials. In my previous life, I built an upper extremity exoskeleton. We were all really proud of it. Same peak lifting capabilities. It was a 15-pound device, and it cost $20,000 to build. There is fundamentally no comparison with conventional technology. We're not talking about we're shifting. It's a completely new ballgame. So why does it matter? How does this mean something? We have arms that we connect to the wall right now for demonstration. What does it mean for you, right? So I'll look at existing solutions. There's two things that make up the weight of existing devices. This plot is basically going to show you weight of devices, and I'm using weight to kind of as a strong parallel to performance. As you get lighter, things get easier. You can do more, things like that. So this is the existing device. This is actually Exo. It's a 55-pound machine. It's about 10 pounds of batteries. 45 pounds of structure and actuation, things like that. And people always say, when you say, we want to build Iron Man, we're making exoskeletons, they say, oh, you need the arc reactor, right? You need Iron Man's little chest thing. I'd love it. I really would. If one of you guys is making it or funding somebody who's doing it, I'd take it. I'm all for it. Problem is, it doesn't actually solve our problem, right? If I had that device and you gave me the arc reactor, magic batteries, it doesn't make my device any really all that much better. So what we're proposing is actually, we're proposing a solution that takes the system and fundamentally changes it. You can think, $40 billion, 30 years of work, making perfect batteries with demonstrated technologies today, we can provide 4 times the benefit that those do to exoskeletons. So that's where we're going. So when we think of the addressable markets, so a lot of people will step up and they'll say, all right, so are you making a niche device, right? Are you doing pediatric rehabilitation? Or are you doing inpatient rehab? I think that that's the wrong way to look at what we're talking about. What we're proposing is we're proposing a technology that fundamentally changes the way you're going to step in exoskeletons. And so every place exoskeletons have an opportunity, we think these apply. So I look at it as a breadth of capabilities. At the one end, you have peak capabilities, which is the military. We're trying to make these people superhuman, do things well beyond what any of us are expecting doing. Moving into industrial, we're talking about maybe not as continuous, but still kind of high load, high capability actions. You move down into consumer applications, you can think elderly assist, you can think hiking, recreational, training, things like that. So this is what we can all do, but we just want to do it better, do it longer. And then all the way down to the other side on the impaired end of the scale, and we're actually improving people's lives, improving capabilities. So we think that we apply to all these spaces. You look at conventional devices, they've only made inroads into inpatient gait rehabilitation. Like I say, that's awesome, but the problem is this is the dream. The dream is far bigger. And if you look at these conventional technologies, they're either cost limited or weight limited or agility limited in every single one of those areas. So I can make strong arguments. We can talk about any of these individual that resonate with you guys of why our technology is the one technology in the world that can apply to these other areas. There are unique benefits in one of these two reasons why traditional devices can't migrate there. So what are we doing about it, right? What does our path look like? So right now, as Saul said, we're on contract to build Iron Man. And so what that looks like for us is we're going to spend the next year moving from our initial proof of concepts into integrated machines. We're going to develop the components, the infrastructure, the basic science that provides us this capability to make this jump. And so that's what we're doing with this project over the next year. From there, we're going to take those as tools and we're going to integrate into initial products, essentially. And so what we're looking at is areas such as industrial assistance, right? $15 billion a year spent on workman's comp injuries for overexertion due to lifting. That's a crazy number that we accept by just paying out the bill. So lift safety for people in industrial environments. Elderly sit-to-stand transitions. The elderly population is growing drastically, and sit-to-stand transitions or stairs are the number one scenario in which people fall and have injuries that lead to significant care costs. So what does the vision for us look like? I actually honestly look at exoskeletons, and I look at a future where exoskeletons are pervasive. They're everywhere in our lives. They're embedded into what we do. They form the standard of care models for the way that we do rehabilitation. They seamlessly blend into the way people go into their world and have assistance to continue to do things better. It's how we play longer, play harder. It's in our jobs. It's in the military to help them continue to do more. And I honestly feel that our technology gives us a unique ability to do that, to actually execute on this dream and for the first time make exoskeletons accessible. Thank you.
I'm not going to say that my job is easy, but I will say that there's one incredibly great part about my job, which is I get to work with a building full of passionate people. And I wouldn't want to compare the people in the building on passion, but the words "I was born to make exoskeletons work" I've heard come from Tim more than once. And really, across the board, our people have the passion to bring these technologies to fruition, and I am inspired myself every day. So in the spirit of what is Otherlab, you're all like, how on earth can this all work? This is my hand drawing that is close to as possible, describes the structure or business model of Otherlab. These are the raindrops of the real world trying to beat down on you. I call Otherlab the umbrella. Under that umbrella, we have ideas, projects, and companies. We'll talk about some very early ideas that we have at the moment that we're working on. Sometimes those ideas graduate into becoming real projects, like some of the projects you've seen. Some of those projects graduate to become the proto companies that you've seen today, like the Volute and New-Buttocks and the exoskeleton work that Tim just talked about. And then eventually, you can see they're getting closer and closer to the edge of the umbrella, and they're starting to feel a few raindrops, and the real world is starting to beat them up, and there's customers and there's investors, and it's getting a little more difficult. And then eventually, as you can see, these two are on their path to graduating. They become wholly independent spin-out companies. So the last speaker today is Danielle Applestone. She is going to talk to you about Other Machine Company. She has graduated to independent status. You've probably noticed that we all here at Otherlab genuinely love machines and computer-controlled machines. Danielle loves not only building those machines, but bringing those machines to people and changing people's lives with those machines. So, Danielle.
Hi, everyone. I totally just thought of a new intro to my talk, so I'm going to try it out on you. So Otherlab is full of people who are amazing and have access to the best tools, and they had great education and great engineering training. And what I want to do is for that to not be a rarity, but that to be everywhere, and I think that we can do it. I'm CEO of Other Machine Company. I have no clicker. Here it is. So Other Machine Company actually started with that vision. We were a DARPA-funded project. We were designing tools and software to bring modern manufacturing equipment to the classroom. And this was great work. I mean, we were like, holy crap, DARPA wants to spend money on schools and bring manufacturing everywhere. That sounds good. But when we got to the end of the project, we were like, we don't need this to just be in schools. We need this to be everywhere, and lots of people can benefit. So that's what we're doing now. Instead of you having to go to a factory to make high precision 3D parts out of metal and wood and even circuit board, manufacturing can come to you. It can be 16 pounds. It can travel with you everywhere, as it does with me, all around town, fundraising. And this is the reality of before Other Machine Company. This is what you had to do. If you wanted to have even like a small aluminum gear made for something you were working on, you had to go here. It's a factory. There's large machines. There's a tiny guy in the middle there. You have to interface with a person who does the design, a person who makes the paths for your idea, a person who runs the machine. This is super expensive, and nobody really has access to this. So we're basically changing all of that. And since we've been shipping this product, we have realized that yes, in fact, everyone is an inventor. Everybody has an opinion about the things that they have in their life. Everyone sees the problems around them and has an idea about how it could be improved. We think that by giving access to high-quality tools and really simple-to-use software is the way that you give all of those people a voice. So this is the voice of some of our customers. These are, you can see there's electronics, flexible electronics. Someone made a robot out of a PCB board, which is crazy. This guy is Kyle. He runs the company One Wheel. It's like a self-balancing skateboard. He also, this is him riding away with his other mill. Oh yeah, it's called the Other Mill. And this is also a new area, so not only engineering stuff, but also craft. Think of Etsy entrepreneurs. There hasn't been a machine designed for those people before, and now that there is one, we see jewelry, we see leatherwork. That's a chocolate. There's all stamp making and print making for, for paper craft and also for fabric, things like that. These people are incredible, and this is one of my favorite examples. This is a guy named Greg Wygonick. He's I don't even know what his job is, but he's not an engineer. So he designed this triangle circuit up in the right. It's a triangle. It lights up an LED. That's it. In the middle, he's moved on to sensors and things like that. And then he gets this idea, which is like, hey, I go through my life, and there's sometimes when I really need to be amped up and I don't want to like rely on coffee for that. I want something else. And he's like, what if I had a metronome on my skin and it could speed up when I needed, when I needed to feel excited, or it could slow me down when it was time like to go to bed. And so he bought a 3D printer and he bought another mill, previous to that, and he started designing it. And I wish you could see his beautiful, clear wearable. This guy in 8 months designed his own wearable, and he's using himself as a guinea pig because he had an idea about something in his life he wanted to change, and he had the means to do it. And that is just like, if I talk about it any longer, I'll cry. So this is also a more robust example. So this is one of our investors bought a machine, decided he wanted to make a car part for this really inexpensive $500 car. So he cut this aluminum flange, to replace the plastic parts. So it's not just for small things or tchotchkes or whatever. It's for real work. And this is kind of the culmination of what we're doing. This is back to our roots in education, except for this is education in Uganda. So we gave a machine to this man named Lindsay Craig and this organization called the FundyBots. This is his makerspace on the go in Uganda. And he is teaching these kids and adults too, how to do robotics and how to design small electronics for things like automatic irrigation and livestock feeding and solar collection and things like that. This is huge. Like, this is probably like the most extreme environment, but it really represents the whole reason why we do this is like manufacturing can be done everywhere. You just have to give the tools to the people with the need. And this is what we see as the future of manufacturing. It's much more distributed, it's ultra customized, it's on demand, and it's really, it's everywhere and everybody can participate. So if you'd love to see the machine, we can cut something for you or, a friend or a kid or whatever, and you can check out some of our stuff in the back. Thanks a lot.
One other really exciting thing around here is that Danielle has just requested her own shipping and receiving department because she actually makes technology go out the door, which is really fun to watch, an inspiration for us all. The other agenda item we have today is we have haphazardly in the past created relationships, whether those relationships be venture relationships or government relationships or even individuals and corporate partnerships. We are trying to make those relationships stronger and a little more purposeful, and so that's why you're all here. So you might be like, okay, that's a cool set of things we've seen now. Now I'm going to show you, give you a little glimpse into what is the future? What are the things that we are thinking about or doing now that might be new things coming up? So Danielle has just showed you, we have a lot of deep expertise in writing in CAD systems and CAM systems for CNC machines. This is actually an interesting project we have just done. In 12 weeks, we went from a blank plate to what you see on the left here. This is an 8-foot wide laser printer that takes 1-ton rolls of plastic and it can create tents, medical devices, and all sorts of things in line. So from 0 to 12 weeks, you can design a bespoke CNC machine that can make an entirely new category of things. As every one of the people who's been on stage today knows, I'm prone to saying outrageous things occasionally. One of the outrageous things I say most often is if you would like to make something slowly and have it be fragile and expensive and go to landfill, you use a 3D printer. That's one version of advanced manufacturing. I think this is the much more exciting version of advanced manufacturing. Take a highly purpose-built tool, like we just showed, use the world's best CAD tools to take a 3D structure, deconvolve that, including a whole bunch of complicated parts inside, like heat exchangers and air exchangers, reduce it to 2D parts, and make it come out of a laser printer. We can build room-sized machines in about 15 minutes on this. You can actually see one of these rooms downstairs. Related to that project is another project we are doing with DARPA, once again in the realm of vocational training and education with CNC machines. We are building a new class of open source. Hopefully electric motorcycles will solve that problem. Actually, I rode that one-wheel electric skateboard the other day. I really hope that that's what solves that problem. We are working with DARPA now, again, on making open source, very low cost, metal cutting laser cutters that you can put in vocational training situations to take real sheet metal and make real physical mechanical objects very quickly, and a whole bunch of software tools to enable that. We're actually using similar technologies to this now, something we are enormously excited about. You may not sound very exciting when I say to people heat exchanger. Turns out 65 to 70% of the world's energy and carbon goes through a heat exchanger. They are ripe for innovation. Turns out what the world is good at today, which we've talked about now, is precision is cheap, manufacturing complexity is cheap. So this is a new class of polymeric heat exchanger. We may or may not have made one work this morning, and you may be able to see that downstairs. So that's something that is really exciting to us in the next year. This is a personal favorite project. Nearly everyone here rides or is passionate about bicycles in some way. We actually built our own four-axis laser cutter to take metal tubes and cut them into the shapes that you see here. So this is in real time how quickly it takes to cut one tube. Bicycle is made out of 8 tubes. So I can now do very, very high precision cutting of the parts for a bicycle in about 10 minutes for an entire frame. Here's the chainstay similarly being cut. We actually, oh, there we go. We actually wrote, it's now possible, we're now writing the web interface for this. This is a bespoke CAD program that takes specifically a bicycle. You enter in your physical dimensions. It automatically computes the optimized bicycle for you. You send that file to the laser. It cuts the laser. It creates all of the joinery. Here are complete frame sets cut. One of these bicycles in the back that you can have a look at. And so the vision now is, so this is about 50% of the bicycle making process done. So now we've, with sub-millimeter precision, actually about 0.1 millimeter precision, cut this. This is an example of it being welded. But the future of this is not being welded by hand. It's actually robots. I guess we're in a race against the sun setting here. This you can see in our other building today. We have a pair of robots. One of them we call Hand and one of them we call Love. So far we're training them to draw on each other. So imagine drawing on your own hand an accurate picture while one hand is moving. So you may think this is already done. Actually, this is the state of the art in industrial robotics. Most industrial robots, you actually have an exclusion zone around them. This is, in fact, what you do to void the warranty on $100,000 robots, because they don't want you to hit them. These robot arms, and this should contextualize the things that Kevin's been doing, these guys, they cost $100,000 a piece, and they weigh 600 pounds, and they have a 15 kilowatt electrical connection. And so that contextualizes the 10-pound robots that he's building. So once you know how to do that, we're actually warming up to doing this. So we're now using a Sharpie marker instead of a laser welder. We're building our own custom laser welder so we can do higher quality welds. And we will now be able to go from you walking in, taking your measurements, to cutting and welding your custom bicycle explicitly to your geometry while you wait. And this is actually, I think, the future of advanced manufacturing. Why is this interesting as a general rule in manufacturing, in advanced manufacturing? Traditionally, if you buy a bicycle, there's a wholesaler for the materials, there's a tube processor, the tube processor goes to the frame builders go to the people who assemble the bicycles, then there's a wholesaler for the bicycles and a retailer for the bicycles. All of them charge a margin. This is margin compression in an amazing way. So now you buy the raw materials and you ship directly to the user the custom product to them, and it looks like we will cost effectively make you your custom bicycle better than the $1,000 store-bought one. And I think this generalizes to an awful lot of interesting areas. Slightly out of left field, but relating to our penchant for horribly difficult-looking equations, this actually was an equation that was based on an idea that really harked back to the 2002 MIT work, is can we make textiles that change their thermal insulation as you wear them? So we actually are proud to announce Brent Ridley, who's here, is launching a program to create, I'll say it even though it's trademarked, better sweaters. So as you wear these things, they will heat up and cool down in response to ambient temperature, so no batteries required, and that's all based on a fundamental physical insight. That's very exciting. And then finally, a little further out, but we are looking at because of our deep experience in CNC machines and mobile robotics. I think this is an extremely exciting area, is automated agriculture, for lowering the carbon footprint, lowering the energy footprint, and really the water footprint of this industry. So I think that's it. I'm on to thank yous. If you're looking for Jim McBride, the CTO, he's the guy who looks like a president. We had tin-type people come and take photos of all the people. This is Henrik, our CEO. He put this all together today, so thank him if you enjoyed it. Send all critique to him, not to me. This is Ali, who makes everything run around. She runs operations and did a great job getting the event to go, mostly according to plan. These are our incredible team leads, or as many as we could fit on a slide, so look for them. And we're not afraid to hide the fact that we have spectacular people. All of our engineers and staff are wonderful. They will all be on hand. Please talk to them. Get the warts and all stories of how research through to product development looks like on the ground. That'd be great. And most of all, thank you to all of you for coming. I hope you enjoyed it. I hope you are full of interesting questions to accost me with as soon as I step off that chair, or any of these people to also handle questions. It's a tradition in Otherlab to have beer o'clock, roughly 4 o'clock on Friday. You can maybe convince us to start early today. I encourage you to visit the demos we have here. I also encourage you to visit at around 4 o'clock. If you stay that late, we will open up the other building for people to have a look. You can see our robots. You can see Danielle's fabulous manufacturing line over there, and Layla's solar cells. Also have a look around downstairs. We might have those heat exchangers and those tents built, and you might want to ask some questions about those. Also, APROE, we have a couple of people who occupy the building with us. Martha and Watson is one of them. Also, Advanced Prototype Engineering. They build the world's best machine shops for people, including helping us keep ours better than it should be. And they also do spectacular prototyping, including helping us rapidly build the machines we build. So they will be here if you are interested in thinking about those things. So everyone, thanks again. Enjoy the beer and the wine. Hopefully it's all here. Half of the wine is here. That's good. I hope you like white. All right, thanks.